Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi, and today we are going to talk on module that is conduction in glasses and its application, and this is under the paper ceramics. So in this module we will discuss about the conduction in glasses, mixed conduction and its application. So before moving further, let's discuss about the conduction in glasses. So the fast ionic conducting, which we are calling at FIC, glasses were discovered approximately 20 years ago, and it was immediately clear that wide range of technological application of these materials. So from that time, an enormous and more or less systematic research effort has been made to synthesize and optimize such glasses matrices having the desired thermal and electrical properties. So without any claims of completeness, this module reviews the large mass of experimental studies and the theoretical background about the transport properties of conducting glass materials, and the ionic conduction in glasses has been observed by Warburg in the last century. So the glasses were also the first solid electrolyte to be used in thermochemical probes, and many cation and sensitive glass electrodes have been reported over the years. However, a characteristic of these glasses was their relatively very high electrical resistivity at room temperature, but the progress in identifying such glasses with higher ionic conductivity has been very slow until 20 years ago, probably because of the lack of the studies about the local glass structures and the inability to isolate carriers and mobile contributions to conductivity. So let us now discuss about the conduction in glasses in detail. Conduction of gases. Gases have a random three-dimensional network and contain glass-forming agents such as SiO2, B2O3 and Al2O3. The interstitial positions are occupied by modifier ions such as Na+, K+, and Li+, or blocking ions such as Ca2+ and Mg2+. Here, Na plus is the sodium ion, K plus is the potassium ion, Li plus is lithium ion, Ca2 plus is calcium, and Mg2 plus is magnesium. The conductivity increases as the temperature increased, as barrier for migration for mobile modifiers is easily overcome by thermal activation. Usually, as the size of the modifier ion decreases, the conductivity increases. And as the concentration of blocking ions increases, the conductivity decreases. Now here comes molten silicates. The molten silicates are now commercial importance as glass melting is typically done in electrical furnaces using resistive heating of glass. So the electrical conductivity is dependent upon the concentration of alkali ions. So here we are representing the alkaline ions as R, which can be Na plus, that is sodium ion, lithium plus, Li plus, and K plus, that is potassium ion. So for R2O greater than 22%, the highest conductivity is achieved for lithium oxide, that is Li2O, followed by sodium oxide, that is Na2O, and then potassium oxide, that is K2O. While for R2O less than 22%, the sodium oxide, that is Na2O, yields the highest conductivity, followed by potassium oxide, that is K2O, and lithium oxide, that is Li2O. So the typical electrical resistivity for soda silicate glasses varies between 10 to power minus 2 to 50 ohm centimeter and depends strongly upon the alkali contents. So the silicates also contain alkali earth ions such as Ca2 plus, Sr2 plus, etc. But the conductivity of alkali earth containing silicate glasses is about an order of magnitude lower than alkali containing silicates. So in alkali earth compounds, the highest conductivity is obtained by incorporating the calcium oxide, that is CaO, followed by magnesium oxide, that is MgO, strontium oxide, that is SrO, and barium oxide, that is BaO. However, the differences are very small. Now comes the fast ion conductors. The materials showing very high conductivities, the several orders of magnitude higher than normal ionic solids. So the conductivity is greater than 10 to power minus 2 per ohm per centimeter at temperatures much lower than the melting points, and the number of charge carrier is very large fraction of potentially mobile ions, which is significantly larger than in a normal ionic compound. Hence, the ion diffusion is solely governed by the diffusion ions energy, and hence the defect formation energy need not be provided, resulting in overall low activation energy for migration. So the first one is the intrinsic FICs, that is intrinsic fast ion conductors. So in these, the halides and chalconides of silver and copper, example AgI is a silver ion, that is Ag plus conductor, whereas the alkali metal conductors such as non-stoichiometric aluminates, typically oxides with alpha alumina structure with highly mobile monovalent cation, example alpha Al2O3 or Na2O 11 times Al2O3. So the second category is extrinsic FICs, that is extrinsic fast ion conductors. So the oxides with fluoride structures such as ZrO2 doped with aliovalent oxides, creating large number of oxide vacancies or oxygen vacancies, and we call it as fast ion conductors such as Y2O3.Zr2O or ZrO2. In these materials, the enthalpy of migration can be as low as 0.01 to zero point 0.2. Let us take some examples of ionic conduction. So the first example is cobalt oxide and nickel oxide, and both oxides are p-type conductors. These are easily oxidizable oxides and are prone to metal vacancies, that is M1-XO, which govern the conduction. The carrier concentrations can be expressed as N is equal to VCO plus 2 VCO double prime. So such type of reactions we have already discussed in the defect reaction in the defect chemistry module. So in these materials, the hole mobility is much larger than the ionic mobility, such that the conductivity is essentially electronic. While Hall measurements can be used to measure the mobility, further, the conductivity measurements can yield the carrier concentration in these materials. Now the next example is mixed electronic ion conduction in magnesium oxide. Now let us work out for the magnesium oxide the various parameters. So let us start. Assume that the temperature is 1600 degrees Celsius for magnesium oxide. So we can estimate the concentration of Schottky defects, which are 1.4 into 10 to power 11 per centimeter cube, concentration of electronic defects and vacancies present for the magnesium oxygen, and others. The diffusion coefficient for magnesium vacancies can be estimated by the expression, that is D is equal to 0.38 into exponential minus 2.29 by kT. At 1600 degrees Celsius, one can calculate the mobility from the Nernst-Einstein equation, and it comes out to be 3.3 into 10 to the power minus 6 centimeters square per volts per second. However, at 1600 degrees Celsius, the mobility of electrons and holes are 24 and 7 centimeters square per volts seconds respectively. So even though the vacancy concentration is larger than the electron or hole concentration, the conduction is dominated by electrons or holes simply because their mobility is order of more than 6 orders of magnitude. However, in reality, magnesium oxide is prone to having purities such as Al2O3 with aluminium concentrations of the order of aluminium concentration of 400 mole ppm. So using the defect reaction, one can calculate the ionic conductivity, which comes out to be 2.4 into 10 to the power minus 5 per ohm per centimeter. However, the electrical or the electronic conductivity can be electron or hole dominant depending upon the partial pressure of oxygen. So one can prove that the electron dominate under reducing conditions while hole dominate under oxidizing conditions. So for example, in normal atmosphere, the partial pressure of oxygen is around 0.21 atmosphere. So in this case, the holes dominates. The hole concentration can be determined using the following defect equation, which is given as half O2 gives Vmg plus OOx plus 2 holes. Here for the mass conservation, we can see that NH is equal to 2 Vmg, and hence the equilibrium constant comes out to be 10 to the power 64 exponential minus 6.24 by RT. So using the above equations, one can calculate the concentration of holes, and it comes out to be 5 into 10 to the power 13 per centimeter cube. Similarly, electronic conductivity can also be calculated using the desired formula, and it comes out to be 5.6 into 10 to the power minus 5 per ohm per centimeter. Now the total conductivity becomes the conductivity of holes and ionic conductivity, which comes out to be 8 into 10 to the power minus 5 Siemens per meter. Hence, so students, you can work out the same thing for the electronic and ionic transference numbers. Electrochemical potential. Usually in ionic systems, both the effects of gradients in chemical and electrical potential on the mobilities are present. Non-uniform distribution of charge defects can give rise to internal electrical field even in the absence of external electric field. So the total driving force for mass transport is defined by the electrochemical potential. The electrochemical potential of species I, denoted by eta, is the sum of chemical potentials, which is given as eta I is equal to mu I plus Zi F phi, where Z is the effective charge and F is the Faraday's constant. Now, the virtual force on the particle is the negative gradient of eta I. So, force is equal to minus 1 by Na into d eta I by dx. So, the flux is equal to C into V, and it comes out to be C into B into F. So, on substituting the values, we get that flux is equal to minus Cb by Na times d mu I by dx plus Zif d phi by dx. Hence, This expression shows that the flux J is a function of electric field, that is d phi by dx. Nernst equation and application of ionic conductors. The ionic transport is essential for the imposed oxygen pressure gradient to establish a gradient in the oxygen concentration. Simultaneously, electronic conduction must be avoided to prevent the short circuiting, which requires Ti is approximately 1. Consider two sides separated by an electrolyte, and at equilibrium, chemical potential of two sides is equal. So, eta I of side 1 is equal to eta I of side 2. So, the electrical potential across the electrolyte is related to the chemical potential difference, which comes out to be mu I of side 1 minus mu I of side 2 comes out to be minus ZIF into del phi. The chemical potential can be expressed as mu I is equal to mu naught plus 1 by 2 RT ln partial pressure of oxygen. Thus, minus ZIF into delta phi is equal to 1 by 2 RT ln partial pressure of O2 minus 1 by 2 RT natural log of partial pressure of O2 of side 2. So, the resultant we get that del phi is equal to minus 1 by 2 RT ZIF into natural log of partial pressure of O2 of side 1 by partial pressure of O2 of side 2. So, this is the Nernst equation. The examples of ionic conductors in engineering applications. The conducting ceramics are used in a variety of applications such as silicon carbide and molybdenum silicide, that is MoSi2, as heating elements and electrodes. ZnO and silicon carbide as varistors for circuit protection. YSZ beta alumina as electrolyte in fuel cells and batteries. Materials like YSZ in gas sensing applications. So while heating elements and varistors utilize the electronic conduction properties of the ceramics, fuel cells and sensors typically utilize ionic conductivity characteristics. So let us discuss it one by one. Varistor or voltage dependent resistors. Varistors are the devices offering high resistance at low voltages and low resistance at high voltages. These are used to protect a circuit against sudden upsurges in the voltage or transients, which you can see in this figure. So, the typically used materials are zinc oxide and silicon carbide powders bonded in a matrix with an intergranular layer that is highly resistive. The current voltage characteristics are governed by the electrical nature of grain and intragranular layers. The basic principle of operation is that the material resistance is high at low voltages and decreases when voltage is increased, allowing excess current to pass through nearby the protecting circuit. Role of grain boundaries. The intergranular layers, that is IGLs, contain defect states whose role is to trap free electrons from the neighboring n-type semiconducting zinc oxide grains. This results in the formation of space charge depletion layer in the zinc oxide grains in the regions and adjacent to the grain boundaries. These boundaries between each grains and its neighbor form a junction showing diode-like characteristics and allowing flow of current in one direction only. So students, you can see the schematic of the electronic structure of zinc oxide grain and intergranular layer without bias and with bias. Operation of SOFC, that is solid oxide fuel cells. So students, on the left hand side you can see the schematic for the operation of SOFC device. So the anode electrolyte interface reaction is O2 minus plus H2 gives H2O plus 2 electron, and O2 minus plus CO gives CO2 plus 2 electron. The reaction at the cathode electrolyte interface is O2 plus 4 electron gives 2O2 minus, and the overall reaction that occur is H2 plus half O2 gives H2O, and CO plus half O2 gives CO2. It must be noted that the high ionic conduction through the electrolyte is required to minimize the resistive loss. Oxygen sensors in automobile exhaust. The process is to first measure the partial pressure of oxygen of the exhaust by using an oxygen sensor. The difference between the partial pressure of oxygen of the exhaust and air can be translated into an electrical signal which is fed as electrical input to the fuel injection system to optimize the air-fuel ratio. So students, you can see the schematic of an automobile exhaust sensor and the potentially generated by the different oxygen partial pressure on the two sides of the electrolyte. So the oxygen sensors are typically conducting ceramics operating on two principles. The first is based on the Nernst effect, where an electrical potential is created when there is partial oxygen pressure gradient across the sensor. Second is where one can measure the variation in the conductivity of the ceramic versus the partial pressure of oxygen. So students, let us summarize what we have learned in this module. So the first thing which we have read, that the open structures lead to low activation energy and hence have high conductivity in materials called as fast ion conductors. Moreover, the presence of composition gradients of charge defects also leads to electrical potential gradients, and this, when combined with the chemical potential gradients, give rise to electrochemical potentials, and these can lead to, or these can be used to apply the oxide ceramics for various applications. The ceramic conductors are used in variety of applications. For example, zinc oxide in varistors, doped ZrO2 as solid electrolytes in fuel cells, and even in oxygen sensors, batteries, flexible batteries, and so on. Thank you.